Now that you have an idea about how the mod operator works, we're going to make some more advanced techniques that we can use for more complicated computations. So we're going to look at some advanced techniques for using the mod operator. We're going to derive two useful tools for doing mod computations, and then we're going to work an example. So suppose we want to compute a mod operator computation that is kind of unpleasant, like say, I don't know, 937,000 mod 6. Here is a useful tool for actually doing that computation. So suppose n is a natural number and a and b are integers, and suppose that a mod n is equal to some number r1, so that's like a remainder, right? And b mod n is equal to some other number r2. Then when you add a plus b and want to take that number mod n, it turns out you get the exact same number as you get by taking r1 plus r2 and taking that mod n. Now you might actually get r1 plus r2, but in case r1 plus r2 goes above n, you have to reduce it mod n as well. And the similar thing works for multiplication. If you have a times b mod n, that is exactly the same as r1 times r2 mod n. So first I'm going to give you an idea about why this is true, and then we're going to use it in that computation of 937,000 mod 6. So if we want to look at a plus b mod n, we want a number that is congruent to a plus b mod n, and that is positive and small as possible, or non-negative and small as possible. So we're assuming that a mod n is equal to r1, and that means that a is equal to r1 plus some multiple of n times k, where k is some integer. And b mod n is equal to some r2. That means that b is equal to r2 plus n times some integer m as well. So if we want to find a plus b, we can actually just plug in those expressions for a and b in that computation. So a plus b is the same as r1 plus nk plus r2 plus nm. If we put the remainders together and we put the multiples of n together as well, we get r1 plus r2 equals nk plus nm. Then we can factor out an n from that last parenthetical statement, and we get r1 plus r2 plus n times k plus m. And notice that is exactly the same as the equation saying that a plus b is congruent to r1 plus r2 mod n, which means that they have the exact same value when you use the mod operator, right? So a plus b mod n is exactly the same as r1 plus r2 mod n. If you do almost the exact same type of computation for n equals ab mod n a times b, you get a very similar type of situation where you end up with r1 times r2 mod n. I encourage you to try it. Try it. If you don't want to, I guess you don't have to, but seriously, you should try it. All right, so now let's see how we can actually use these techniques for doing 937,000 mod 6. What those computations basically say is that you can replace any number that is either added or multiplied by its reduction mod 6. So for instance, if we wanted to factor out 937,000 into 937 times 10 times 10 times 10, right? Each of those 10s, if you take those computations mod 6, you get a remainder of 4, so you can replace each of those with a 4. And already we have a much smaller number. Now, if we multiply all those 4s together, we get 64. If we take 64 mod 6, 6 goes in there 10 times with a remainder of 4. So you can replace that with a 4. So you have 937 times 4. Now we can mess around with the 937. If we want to use addition on that, we can do 900 plus 37. And if we look at that 37, we can replace that with its computation mod 6. 37 mod 6, well, let's see. 6 times 6 is 36 with a remainder of 1. We get 900 plus 1 instead. If we play around with that 900, that is 90 times 10. 90 itself is 6 times 15, so that 900 is actually a multiple of 6, which means we get a remainder of 0. So 900 mod 6 is actually 0, so we get 0 plus 1 times 4, and even on a bad arithmetic day, I know that's equal to 4, and that's our final answer. So without having to do much complicated computations, we can get down to that mod operator, even though it looks pretty nasty. So now I encourage you to use those techniques on the activities. The name of the PDF file is More Mod Operator.